Welcome to the exercises for Chapter 7. This chapter focused on rules of differentiation, like the product rule, the chain rule, the quotient rule, and lots of other fun rules in differential calculus. And the goal of this first exercise is to test whether the derivative of function f times function g equals the derivative of function f times the derivative of function g. Now, here you see a not equal sign, and you know from the product rule that this inequality actually is true. So it is true that these two expressions are not equal. This is not how differentiation works on the product of two functions. And so in this exercise, you are going to demonstrate that these two expressions are not equal. And then in the next exercise, in exercise 2, you will confirm the actual product rule. Okay, so here's what you want to do. You want to write SymPy code that will produce an output that looks like this. Let me zoom in a little bit here. Okay, so here you can see we list three functions, f of x, g of x, and h of x. And so what you want to do is implement these three functions as symbolic expressions, so as SymPy variables, and then calculate the derivative or use SymPy to differentiate each of these functions individually. And it takes, only a couple of moments of your time to confirm this derivative and this derivative for f of g. You can see that h of x is actually just the product of f and g. And so, in fact, the way that I implemented this in SymPy is to define h to be f times g, as opposed to writing this out individually. Okay, so then you want to differentiate h, and that works out to be this. And then you want to differentiate f prime, not differentiate, but just show the product of f prime and g prime. And you'll see that these two are not equal, which is one demonstration of this fact here. Okay, and then over here in panel B, show exactly the same functions. Our f and g are exactly the same functions, but now h is created by summing f and g. So you can see that here instead of multiplying them together. Now, you learned in a previous chapter about the linearity of differentiation, and so f prime plus g prime actually is equal to h prime, right? So this is just a counterexample to show that just defining some function by two other functions actually does hold for this property. So h prime does equal f prime plus g prime, but it's not. It doesn't work that way for multiplication. Here we need to use the product rule. So here's what the code looks like. I call this exercise checking the product rule. We're actually demonstrating where the product rule does not apply, or where multiplication does not apply, and we need the product rule. Anyway, so here I'm defining x to be a symbolic variable. These are the two functions, f and g, and then you can see I'm defining function h to be just the product of f times g. Okay, and then here I compute their derivatives. I'm using variable p for f prime. Sometimes I use df for the derivative of f, and here I'm using p just for a little bit of variability, just give you some options for variable naming conventions. Okay, so here you can see I'm printing out or calculating the derivative in SymPy of each of these functions individually, including h, which is the product of f and g. Okay, and then here I'm printing this out. So each of the three functions, and then the derivatives for each of these three functions. And here at the bottom line, I am printing the derivative of f times the derivative of g, okay, just like this. And now you already know what to expect, partly from reading the chapter and partly from just listening to my introduction to this exercise in the book. Basically, the key point here is that h prime is not equal to f prime times g prime, okay? So the derivative of the product of two functions is not the same thing as the product of the derivative of the individual functions. Okay, and then, so this was what I showed as panel A in the book figure, And now to show panel B, all we need to do is, if you want, you can copy and paste this code into a new cell. That's also fine. I'm just doing this manually by changing the multiplication into addition. So this is here. Actually, this should also be like this, f plus g. So this confirms the linearity of differentiation, which is a property of derivatives that you learned about in the previous chapter. Now in exercise 2, we will confirm why the product rule actually works. This is not a proof of the product rule. I gave that in the text of this chapter. This is a nice demonstration using symbolic calculations in SymPy. Okay, so what you want to do is in SymPy, basically produce output that looks like this figure here. So we have two functions, f and g. F is x squared, and g of x is cos of x. And then you create a new function by multiplying these functions. Very simple. Okay, and then what you want to do is show that the derivative of the product of these two functions is, all this stuff. And then you want to implement the derivative of the first times the second plus the first times the derivative of the second. Okay, so this is a calculation that you are going to implement manually in SymPy by directly writing out the derivative of f times g plus f times the derivative of g. And then, this line comes from taking the product of these two functions first, and then differentiating that resulting expression, that resulting function. Okay, and then basically if the product rule is true, which we know it is, if SymPy correctly implements the product rule, then these two expressions here will be identical to each other. So here I create a symbolic variable. Here I create the two functions, f of x and g of x. Here I calculate their derivatives individually, separately from each other. And here I create a new function. I just call this fg. And that is equal to the product of these two functions. Now, you could also call this function h, like I did in the previous exercise. These are all, it's all fine. Let's see. And then I take the derivative of the product of these two functions. And here's where I'm implementing the product rule manually. So the derivative of the first times the second plus the first times the derivative of the second. And then I call variable man for manual, derivative of f times g. Okay, and then here I'm just using LaTeX coding in combination with the display math function duo to print out all of these results. Again, nothing too spectacular here, but you see that these two results match, which means that is a demonstration of the correctness of the product rule. I hope you enjoy working through these kinds of exercises. They are not super difficult, but I think it is useful to improve your SymPy coding skills and also to reinforce how the product rule works. Exercise 3 of Chapter 7 continues along the lines of exercises 1 and 2. So it's a very similar situation, but now we are going to confirm the quotient rule. So we did the product rule and now for the quotient rule. So this is the same two functions as in the previous exercise. So again, what you want to do is separately define function f to be x squared and function g to be cos x. And then you want to calculate the derivatives of f and the derivative of g, all of this done in SymPy. And then you want to create another function that is f divided by g. And then the idea is to compare the derivative of f divided by g with the manual implementation of the quotient rule, which you'll remember is f prime times g minus f times g prime divided by g squared. Okay? And now what we should see, if the quotient rule really is correct, and if you haven't made any little coding typos, then this result and this result should match exactly. Okay, and now when you look at these, it's obvious that at least typographically, they do not match exactly. They look a bit different from each other. Okay, so then the question is, why are these different? And are they really different? Or do they just appear to be different? Well, you can probably guess that the answer is that they just appear to be different. Okay, so then what you want to do is take this result here from the manual implementation of the quotient rule, and then use a function in SymPy called sim.simplify. This is a pretty useful function to know about in SymPy. It's basically going to take a symbolic input, like a function that looks like this, and SymPy is going to basically massage and rework and factor and separate and combine and like work with this function in different ways to try to simplify it as best it can according to, whatever principles of simplification the developers have built in. Basically, that involves reducing the number of terms. So here is the output of sim.simplify on this expression here. And you can see that, this has more terms and this has relatively fewer terms. But that didn't really help with our initial confusion, which is that these two expressions look different from each other. Now we've made life even more complicated because we now have three expressions, this one and this one and this one. And in principle, they should all be exactly the same, but they look different. Okay, so that leads us to the final part of this exercise, which is for you to get out a pen and a piece of paper or a crayon or whatever you like to do math with, chalk on a chalkboard if you have that available to you, and basically do some algebraic manipulations to show that these three expressions really are the same. You want to manipulate these expressions so that you can get from any one of these three to any of the other of those three. Okay, so here is the Python code for solving this exercise. Now, notice I'm not defining f or g here. I'm using the same functions that I defined in exercise 2. So you will need to run the code for exercise 2 to define these variables that are used in exercise 3. Okay, so here is the combination of these functions. It is f divided by g, and then I take the derivative of that function. And then here's the manual implementation of the quotient rule. You can see it's the derivative of the first times the second minus the first times the derivative of the second divided by the second squared. All right, so, and then, well, here I just commented out these lines to print the original functions again, just because they're the same as the previous exercise. Okay, so this just reproduces exactly what I showed in the book. Again, this output here, this output and this output, in theory, should be exactly the same. They look initially different, so let's see what happens when we try to simplify. This is also what I showed in the book. Okay, this is the end of my work for this video. I'm not going to show how to work with these equations that you have to do on with a piece of paper and a pen. But it's actually not so difficult. And in fact, you can look at these and see if you break up this cosine squared into cosine, that's going to allow you to separate these terms. You can combine terms and so on. Here we are in exercise 4 of chapter 7. So in the previous 3 exercises, we used SymPy to investigate the product rule and the quotient rule and addition, which just shows the linearity of differentiation. And now in this exercise, this is the last one in this series of confirming the rules of differentiation, we are going to focus on the chain rule. Now, in some sense, this exercise is conceptually simple. It's basically the same as what we were doing in the past couple of exercises. But this one is a little bit more involved just because the SymPy coding is a little bit trickier. It's a little bit more difficult. There's more kind of working parts in this exercise. So let me see. I'll just show you what the output should look like. So you want to write SymPy code that will produce output that looks like this. So we start by defining 3 functions, f of x, g of x, and h of x. And remember that the word log here is for the natural log. SymPy writes out the word log when it's referring to the natural log. Okay, so then you want to create composite functions. So let's start with 2 variables or 2 functions. we have the composite of g inside h. Okay, so you create a new function that is f of g of x, and then you print it out. It looks like this. Now, to implement this composition in SymPy, you use the .subs method, just like I showed a couple of chapters ago when I introduced composite functions and composing functions in SymPy. Okay, and then you want to take the derivative of this composition, and it ends up looking like this. Okay, and then you want to confirm the chain rule using SymPy by comparing this derivative, this differentiation, to the differentiation on the composite functions individually. Okay, so you take f of g and then differentiate that times the derivative of g. And that's going to look like this. This is the output. Now, if the chain rule is correct, and if SymPy correctly differentiates, then we would expect this term, this result, and this result to be exactly identical to each other. So in principle, these two should be the same. Similar to the previous exercise, when you first look at these two results, they appear to be different, but your next goal is to figure out whether these are the same. And here's the spoiler, they are identical, but they just have like slightly different terms worked out. You can see there's a 3 pulled out here. So just confirm for yourself that these two expressions really are the same, even though they initially look to be a little bit different. Okay, so that is for the composition of one function inside another function. And now the next goal in this exercise is basically the same thing, but now we are going to work with the composition of 3 functions. So you want to create a new expression, a SymPy expression for this composition, f of g of h of x. And then you print it out and it looks like this, okay? And then the derivative of this whole beast, this 3-function composition, is this monstrous beast, whatever the hell this thing means. And then what you want to do is, again, write out the chain rule manually, implement this manually in SymPy. So the composition of f or h in g in f, and then that derivative of f with these two functions composed, times the derivative of g with h composed, times the derivative of h. Okay, so this is the chain rule for 3 functions composed in each other. And again, yeah, this result here and this result should be exactly identical. They look initially like they are different from each other, but they're really not different from each other. But now it is your task to take out a piece of paper and a pen, write down these 2 expressions, and make sure you can get from one to the other to convince yourself that these really are identical expressions, even though they initially look like they are different from each other. Okay, so here I am defining these 3 functions, f and g and h. And here's where I'm calculating the individual function derivatives. So the derivative of each of these functions completely separately from each other. So I'm not composing any of the functions just yet, okay? And here is where I actually create the composite functions. So g inside f, I do that by writing f.subs, and then wherever SymPy sees variable x in expression f, we substitute in expression g. Okay, so that is how we create composite functions in SymPy. If this looks strange, then you might want to go back and consult the code and the text for chapter, I think it was chapter 3, where I discussed composite functions. Okay, and then here is our other composite function with 3 functions. So here we are taking h and embedding it inside g, and then we are taking that composite function and embedding that inside f. All right, and then here is where I'm showing the manual chain rule. Here's where I'm calculating. Actually, I'm not showing it yet. So we have the derivative of f, and then we are substituting in g, times the derivative of g apart from any other functions. All right, and then here's the manual implementation of the chain rule for 3 variables. It's a bit complicated, but I think if you look through this carefully and, look at each piece individually, you will see how that maps onto the mathematical expression of the chain rule. Okay, so here I'm taking H, embedding that inside G, and then embedding that inside not f of x, but the derivative of f. Okay, and then I multiply that by the derivative of G, but that is substituting in for H, and then I multiply by H. Multiply by d of H, the derivative of H. Oof, stuff gets very complicated just to talk about. Okay, I hope that all is straightforward and you can see how the SymPy code maps onto the mathematical expressions that I showed in the book. Okay, let me run that code. And then once you get that, so, if this code weren't complicated enough, now it gets even weirder because we have to put all of this stuff into LaTeX expressions to be displayed into the notebook output. Okay, so this part is straightforward. I'm just showing all the individual functions. And here, let's see. Yeah, I mean, the main thing to notice here, this slash left is to get a dynamically sized bracket on the left, and that goes with this one on the right. So f of g of x, and then differentiate that, and that is sim.diff f times g. So this is the variable that I created in the previous cell. Okay, and then here is the manual derivative by implementing the chain rule directly. So this is for the 2-function composition, and here's the same thing for the 3-composition function. Again, the LaTeX coding looks a little bit more complicated, but you can see this is basically just calling the functions that I have already defined here. Okay, so let's print this out, and I'm not going to go through this in depth because I already did when I showed the book text. Okay, and again, these two expressions, so this result here and this result here, really are the same, and you just need to work through it a little bit on a piece of paper with a pen to convince yourself that they really are the same expressions. Welcome to exercise 5 of chapter 7. This exercise, and also the next several exercises, focuses on implicit differentiation in SymPy and also using numerical approximations in NumPy. So let's begin with this exercise using SymPy. Here we have an implicit expression, x cubed times y squared minus 5x to the power of 4. And what you want to do, for starters, is to use SymPy to convert this expression from implicit form into explicit form. The correct answer, the result that you should get SymPy to give you, is y equals plus or minus the square root of 5x. Now, this right here is not a function formally, right? It's not formally considered a function because it fails the vertical line test, right? So there are multiple values of y for the same value of x. So what you need to do in SymPy is get two separate expressions that are both considered to be functions, okay? That's the first part of this exercise, basically to implement this expression in SymPy and solve for y to get two answers that are valid functions in SymPy. Okay, so that's part 1. Part 2 is to differentiate 3 functions. Okay, you want to differentiate this function here using implicit differentiation, and then split this function into 2 and then differentiate each of those separately. And then you can print out the results, and that's going to look something like this. I'll zoom in here. So this is a screenshot from SymPy, so your results should look exactly like this. Here we have the implicit differentiation from implicitly differentiating this expression over here. That's going to look like this. And then when you translate this expression into a explicit form, you get a result like this. And then you're going to get two results here, one for the positive square root and one for the negative square root. Okay, so creating this output in SymPy is part 2 of this exercise. And then finally, part 3 of this exercise is to generate a figure that looks like this. And here we are plotting the positive and negative of the function and the positive and negative of its derivative. So 4 functions in total. And that's because this one expression needs two formal functions to capture both the positive and the negative aspect of the square root function. So here I am creating two symbolic variables, actually in a slightly different way from how I sometimes create symbolic variables. Here I'm importing variables x and y from sim.abc. This is just, I'm just giving you some different options for how to create these symbolic variables in SymPy. So here is the expression in its implicit form. It's implicit because the y's are multiplying the x's on the same side of the equation. And now here we can solve for y. So the trick to solving for y is to use sim.solve, and you put the expression on as the first input and the variable that you want to solve for in the second input. Right now, very often we've been using sim.solve to solve an equation for 0, right? But that's not what we want to do here. We want to solve the equation for y. This is how you can solve for one variable in a multivariable function. Okay, and then it turns out that, actually, before I get to this printing stuff, I'm just going to write x per x comment out this, just to show you what this variable looks like here. So sim.solve actually found two solutions to this equation for y. And so the result here, this variable, this output of sim.solve, is a 2-element list. And here you can see the two elements of this list are nearly exactly the same, except this one has a minus sign. Okay, and so that is how we get two solutions to this equation for, and each of these is a valid function on its own. Okay, so then I'm just printing these out. I didn't actually show this in the book figure, but yeah, here you see the functions. Okay, so now we want to differentiate these three expressions, right? So we have this expression from the explicit form, and then we have the implicit form like this. Okay, so you already know how to use sim.diff, and then the new function to use here, which I explained in the book text, is sim.idiff, where the I, of course, stands for implicit. So we are implicitly differentiating this function. Here is the implicit, this is the variable we want to solve for, and this is the key variable, the independent variable x. Okay, so then I'm printing out these two results here. All right, and this replicates the figure in the book. This little bit of code here is not related to any specific instruction in the exercise. I just thought it would be interesting to explore and to show you how to basically substitute in for y for the implicit form of the function, right? So we have this implicit form here. We have y prime on the left, and then we have variable y on the right. But because we can actually solve for the explicit form, we can optionally substitute in for y the expression, the explicit form of y, which is this. Okay, and that's just what I show here. This is just, linking the concepts that I illustrated in the book, in the text, to working with the SymPy code. Okay, anyway, so on to part 3 of this exercise, which was basically just to plot all of this stuff. I hope you didn't struggle too much with this part. Basically, we have the symbolic expressions, and here I chose to use substitution in combination with list comprehension rather than creating lambda functions, so using sim.lambdify. And that's partly just an arbitrary personal choice, but also, the reason why I did this is that we need this numerical evaluation. We need to get a vector out of this result only exactly once. We do not need to use these symbolic functions multiple times. And so, yeah, if you're only doing it once and there's not too many numbers to evaluate and substitute, then in my humble opinion, it's easier just to have a list comprehension rather than creating a new function, writing extra code. Okay, yeah, and then here's how that function looks. Here we are with exercise 6 of chapter 7. We are going to continue exploring using SymPy to work with implicit functions and implicit differentiation. And then we will also bring NumPy into the mix with numerical approximations to find pretty good solutions when SymPy is unable to give us exact solutions. Okay, so for starters, implement this equation in SymPy. And when you create this variable y, make sure to create variable y, symbolic variable y, as a function of x. So make sure that SymPy understands that y is not just any random symbolic variable, but in fact, y is a function of x. Okay, and then see if you can get SymPy to transform this equation into an explicit function. So something like y equals, and then, terms that only have x. So all the y's on one side and all the x's on the other side. That would be the explicit form. See if you can get SymPy to transform this expression into its explicit form. Okay, and then you want to use NumPy and Matplotlib to find solutions to the equation, so to this equation, solutions to this equation, and also solutions to the derivative that you will get from SymPy, explicitly or implicitly. You will have to figure out how to get the how to differentiate this in SymPy. Okay, and then, basically in NumPy and visualized in Matplotlib, use the grid search method that I introduced in this chapter to find solutions both to the function and to the derivative. And then you are going to find something interesting, which is that there are solutions to the derivative, but there seem not to be any solutions to the function, as evidenced by the absence of black dots in this plot here. So you're going to have to think of why that is the case. Why are there no black dots? Why are there solutions to the derivative? And I will have a small discussion about this point when I show the code. Here I'm creating x as a symbolic variable. This is nothing new here. And here is the slightly new piece of code here where I'm defining y, variable y, not just to be a generic symbolic variable, but explicitly a function, or I'm explicitly telling SymPy that I want y to be a function of x. And this is the syntax for that, also something I introduced earlier in this chapter. Okay, here we have the expression. You can see this doesn't look exactly like how I showed the equation in the book, because there I said equals, so e to the x squared plus y squared equals x plus y. So essentially what I'm doing here is creating this function to be equal to 0 implicitly. So there is an equals 0 that is not explicitly written out, but it's kind of implicit in there. Okay, so then we get the derivative here. And here, what I want to do is see if SymPy can solve for x in this implicitly described function. So let's run all of this code. Actually, first let me run this just to show you. This worked. It was also extremely fast. Here, I'm just going to print out the expression itself. And here is the form for the derivative. So here we see the derivative of this function. Now, every time a SymPy prints y, it also prints parentheses x afterwards. This is actually a more accurate way of describing or writing out this function compared to what I showed in the book, right? Because y really is a function of x. And so it is appropriate to say y of x every time there is y. But just for convenience in the book, and this happens, not just me doing this. This is generally how mathematicians write textbooks and papers and so on. They will just write somewhere in the text that y is a function of x, and then they omit this parenthetical here just in the interest of space. Anyway, the point that I really wanted to mention is that SymPy has no problem differentiating this function implicitly, right? But now the question is whether SymPy can find an explicit form for this function. So I'm going to run this again, and now we get an error message. And the error message is basically no algorithms are implemented to solve this equation. So SymPy does not actually is not able to solve this equation. Sometimes that means that SymPy just isn't clever enough to solve a solvable expression, but in this particular case, it happens to be impossible to solve this expression for y to create an explicit form. So we can only work with the implicit form of this function. Okay, so we have the derivative. And now here I'm going to use the grid search method to find approximate solutions to the equation and to the derivative. So I'm using 1,000 points between 0.5 and 2, both for x and for y. Here I am lambdifying the function and also its derivative. And then here's where I'm evaluating for the function. So I evaluate the function for the x and y grid coordinates, and then I try to find the solutions for where we have a zero of less than a tolerance. Okay, so in principle, in theory, we are looking for z equals exactly 0. Those are the exact solutions to this equation. But as I discussed in the book, in this chapter, and also in previous chapters, when you are approximating solutions to an equation using numerical methods like grid search or like gradient descent or using Newton's method, which you'll learn about in a few chapters from now, it's rare to find exact solutions. So instead, you want to look for solutions that are pretty good, or at least good enough for whatever is your application. And so here, that's why I have this tolerance. So in theory, we want where z is exactly equal to 0. In practice, I'm looking for where z is smaller than 0.001. Arbitrary tolerance number. You can try playing around with this number and see what happens to the map of solutions when you have a smaller tolerance versus a larger tolerance. Okay, anyway, and then here I'm repeating exactly that same code for the derivative. And then here I'm making a plot. So all of the values that solve the xy pairs that solve the implicit form of the function and its derivative get drawn as black dots and as plus signs. All right. And you already know what's going to happen here. Which is that we get solutions for the derivative, but we don't get solutions for the function. Why does this happen? Well, the reason why this happens is that there are no solutions to this function. Let me go back up to this function here. So basically, x and y, there are no values of x and y that make this equation true, that satisfy this equality. And the way you can think about this is that x and y here are squared, and then we are putting them inside, as the power, as the exponent of e. So that means that this left-hand side of the equation is growing really, really fast, and this side of the equation is growing only linearly. So the left-hand side of the equation grows so much faster than the right-hand side of the equation that basically these two sides of the equation can never be equal. There are no pairs of x and y values that can make this expression be true. Certainly not in the domain of real numbers. Okay, so that means that the function has no solutions. But curiously, the derivative does have solutions. And so what does it mean for a function to have no solutions, but the derivative to have solutions? Well, it's just a weird thing about math that, SymPy and NumPy and Matplotlib, the computer doesn't know that, we shouldn't have any solutions here in the derivative because the function is undefined at those xy values. That's something we know. That's something you know. As the calculus expert, you know that the formula for the derivative is not just some random arbitrary formula. It's derived from the original function. And so you cannot consider points in the derivative where the function does not have any valid solutions. So that is something that you would have to know and bring that knowledge into solving problems like this. I also discussed exactly the same concept, but for single variable functions in a couple of chapters ago. Exercise 7 is both conceptually and in terms of code a direct follow up to the previous exercise. So make sure you've solved exercise 6 before starting to work on this one. In fact, in my code solution, I use all the same variables and functions that I created in the previous exercise. Okay, so remember in the previous exercise, we were looking for solutions to this expression here. Actually, let me scroll up. We were looking for solutions to this equation here. And the way that we implemented this is by reformulating this equation to set it equal to 0 and then call that some other variable. And that looks like this. So effectively, this is what we were solving. And then what we were looking for as solutions to x and y were xy pairs that make z equals 0. Okay, so that is to find solutions, but that doesn't mean that we can't just look at the value of z for whatever numbers it happens to be. So that's the idea here. So instead of thinking about z as only a sort of a trick for finding solutions to this equation, instead we are just treating this whole thing as a two-variable function set to z, and then we want to see what the values of z look like over different values of x and y. Okay, so that's basically the goal here. You want to calculate z again, or you can reuse z from the previous exercise, but now visualize all of z as a heat map instead of looking for only the specific xy pairs that make z approximately equal to 0, right? So this is what we did in the previous exercise, and now here we're just going to make an image of z as a heat map. Okay, and then one little extra thing to do here is to transform z to be the absolute value of z and then minus the logarithm. And why am I doing that? Well, I encourage you not to do that, just to visualize z on its own and see how it looks, and then compare that just purely visually to minus the natural log of the absolute value of z. And what you will discover is that taking the minus natural log of the absolute value of an error function just increases the visibility a little bit. So it just makes the tiny, tiny numbers and the really small differences easier for us humans to visualize. And so therefore, minus log transforms are commonly used in optimization problems and machine learning. It just helps algorithms and humans make clearer distinctions between very, very closely spaced small numbers. So the code for this exercise is actually not so involved. In fact, you can see I'm not doing any math coding. There's no math coding anywhere in this exercise because I'm using all of these variables that I created in the previous exercise. Okay, so basically all I'm doing is using IMShow to look at the image of the Z matrix, which is the for the original equation, and dz for the derivative of the equation to find the derivative values. And here I write minus the log of the absolute value. As I mentioned a moment ago, I encourage you to try multiple different ways of visualizing this. You can just visualize z. You can try visualizing the absolute value of z. You can try just the log, so plus the log instead of minus the log. You can try, maybe square root is also interesting to look at. Lots of options. There are reasons why minus the log is commonly used. Some of that is just convention in machine learning because, other people use it. And so therefore you continue to use it just to make your graphs and your algorithms more similar to the rest of the machine learning literature. And if you get into the mathematics of machine learning and statistics, you will also learn other more kind of deeply mathematical, rigorous reasons for preferring minus the natural log of some value. But I'm not going to get into any of that discussion here. Okay, so effectively, this code is just going to reproduce what we saw in the book figure. So this map of this function is all black. And here we see the derivative is mostly black. And then we have this kind of beautiful, really elegant looking stripe of white, which, looks a bit like a Gaussian rotated on its side. It also gets kind of fuzzy here, which means it's slowly getting darker. And here it's slowly getting lighter, and some interesting dynamics here over this two-dimensional plane. So what do these values mean? Well, remember that we are taking minus the log of this value of z, of this solution matrix. So smaller numbers in the solution matrix, which means numbers closer to 0, when you take the log of those become strongly negative, and then we flip the sign so they become positive. So this means that whiter colors here indicates closer values to the solutions to the equation and its derivative, whereas darker values indicate values that are further away, meaning that they are worse solutions or less close to being solutions to the equation and the derivative. So the fact that this map is completely saturated at black is just yet another demonstration or visualization of the fact that there are no solutions to the equation that we started working with in the previous exercise. Welcome to exercise 8 of chapter 7. In this and also in the next exercise, we will explore L'Hopital's rule, and in particular, focusing on L'Hopital's rule in SymPy. So implementing this procedure in SymPy. Also, we are going to have a little review of the quotient rule from differentiation. We're going to get back to limits in SymPy and look at visualization from SymPy objects and translating that into NumPy code in order to get it into Matplotlib and so on. Lots of things to review in this exercise. Okay, so earlier in the chapter, I gave this example of this function, x squared times the natural log of x. And the question that we wanted to know is, what is the limit as x approaches 0 from the right? Now, theoretically, it does not make sense to talk about the limit as x approaches 0 from the left, from negative numbers, because the natural log of 0 cannot be negative. Okay, so what you want to do is implement this function in SymPy, and then you are going to calculate the limit as x goes to 0 in SymPy of this function. Okay, and then you want to create separate variables for f and g, as I discussed earlier in this chapter for applying L'Hopital's rule to this function. And you'll remember from earlier in the chapter that the way that I have written out this function here is not actually valid for L'Hopital's rule because we need a ratio of functions. So in the book chapter, I discussed how to transform this function here, x squared times the natural log of x, so that we actually can use L'Hopital's rule. Okay, so do that, and then this is just a little bit of a review from a previous chapter. I want you to demonstrate empirically in SymPy, using this function, that the derivative of f divided by g is not the same thing as the derivative of f divided by the derivative of g. This is a counterexample for the quotient rule, right? So this is not true. This equivalence here, or the inequality, is true. This is just a bit of a review of the quotient rule. Okay, so once you've solved this part of the exercise and calculated the limit, then I want you to create a plot of this function in Matplotlib. And you can see the range, or the domain here, is 0 to 1, or not literally exactly 0, but some number very, very close to 0. And you'll see that this function has a dip here. So then the last part of this exercise is to use SymPy to find the exact minimum point here and then plot it. Okay, so to do that, you need to find the critical point of this function and then draw that point here. So here I create a symbolic variable for x. Here is the function, x squared times the natural log of x. And here I define the two individual parts to this function that will allow us to use L'Hopital's rule. Now that's the theory. We don't actually need to apply L'Hopital's rule here because SymPy is going to just calculate the limit, as I will show you in a moment. But this does allow us to disconfirm the quotient rule in the next cell. So I'll get to that in a second. Okay, so we can run this code here. I'm calculating the limit as x goes to 0 from the plus side, so from the right, from numbers that are just a little bit larger than 0, so positive numbers. Now, here you can see this comment here. Strangely enough, this also works when we come in from the left. So SymPy tells us that the limit of this function as we approach 0 from the left, from negative numbers, tiny numbers that are negative, is 0. Now, in theory, this kind of is the answer that we're looking for, but in a strict sense, this is not the correct answer, because the correct answer is that there is no limit coming from the left, because because negative numbers are not allowed inside the natural log function. And this also, continues to happen if we would say, if we would restrict the domain or the field of x to be real numbers. We can still get a valid result, the expected result, even if we have only real valued numbers here. Anyway, it's just a little quirk in SymPy, I guess. Okay, so here I differentiate the function. Here I differentiate the numerator, and here I differentiate the denominator separately. And here I'm going to print out the, let's see where it is. We have the derivative of the ratio of functions, and that is not going to be equal to the derivative of the numerator divided by the derivative of the denominator. Okay, so again, the point here is that this term and this term are not the same. They're different from each other. And that is exactly the outcome we would expect from the quotient rule. Okay, very nice. So here I solve for the critical point. I do this before showing the figure, just because then I have the plotting code in the figure. Okay, so we find the critical point by setting the derivative equal to 0 and solving for where x equals, where x gives us a derivative value of 0. And here's what we find here. So the critical point in this function is e to the minus 1/2. That is the x-axis value. And then here we have the y-axis value, and I can print this out here like this, min x and min y. And here we see, so this line is coming from here, printing out the symbolic answer to the critical point. And here I've just converted this into NumPy, so into a floating point number. So e to the minus 1/2 is approximately 0.6. That is the x-axis value for the critical point, and the critical value at the critical point in the function we obtain by substituting the critical point in for x. And yeah, then that gives us this result here. So the critical value happens to be e to the minus 1 divided by 2. Okay, and then I'm plotting here. You can see that we cannot start the plot at 0. Actually, we can, but it doesn't really make sense. And then we get a warning message, because then we have the log of 0. Okay, so that's why I start it at some small value that is a little bit greater than 0. Okay, and now here I'm plotting the critical point. Now, how do we know that this is a minimum? Remember, from the previous chapter on critical points, I discussed that just finding a critical point doesn't tell you the nature of the change in the function behavior at that critical point. You need to do further evaluations. You need to visualize, you can do tests, you can do the first derivative test, for example. And here I've done none of that. Well, I did visualize, but I didn't do the first derivative test. And so how do I know? How am I so confident that this point here, this critical point, really is the minimum of the function? Well, when we look at the function value, the function definition, we can see that whenever x is greater than 1, then these two terms are positive. So we have a positive term multiplying another positive term. So as x increases larger than 1, this function is just going to blow up. And in fact, it blows up to infinity after, over here. This line continues going up. But in between 0 and 1, we have x squared, which is still positive numbers. And the log of a number between 0 and 1 is a negative number. So there we have the product of a positive number and a negative number, which means that the function values are going to be negative. So all of this, and we know that the limit as x goes to 0 is 0. So in between 0 and 1, there's going to be negative numbers. That's the only place in the entire function where we have the possibility for negative numbers. So therefore, the critical point must be a minimum here. All right, and yeah, after 1, the function continues to increase. This is actually a really, really tiny decrease of negative numbers, and you can see that if we go up to like 10. So if we plot x out to 10, then you will see this initial dip. So here's, this is 2, so marker 1 is going to be around here. You don't even see a decrease here, right? We saw a decrease when we zoom in, but now the function grows up to infinity so fast that, we just don't see any dip at all here. Welcome to exercise 9 of chapter 7. Here is an interesting question. We consider the two functions x squared and e to the x. Now, as x goes to infinity, both of these functions also go to infinity. So the limit as x goes to infinity of both of these functions is infinity. But that's not the question here. The question here is which one goes to infinity faster? So imagine a race between x squared and e to the x, and the question is, who goes to infinity faster? Okay, that's the question that we want to answer in this exercise. Now, maybe you have some intuition, maybe you have an idea about which one goes faster. Now, maybe you want to take an empirical approach. You can calculate x squared and e to the x for various values of x, like x equals 10, x equals 100, x equals a billion. And you see, what is a billion squared versus e to the billion? Now, that's fine. Intuition and trying a couple of values, that's a great way to start thinking about this question. But ultimately, we need to take a more rigorous approach to answering this question. We need to have firm evidence, not just some intuition. Okay, and that we're going to use L'Hopital's rule to answer that question. So if you would like to come up with a solution on your own, then please stop listening. You can pause the video now. Otherwise, I am going to explain how to set up this solution here, how to set up the problem here. Okay, so the trick here is to consider that whichever one of these two functions grows faster, if we set the ratio of these two functions, then that ratio is either going to go to infinity or to 0, depending on which of these two functions grows faster. Okay, so in particular, consider f of x equals e to the x and g of x equals x squared. So now we can define a ratio between these two functions, and we consider the limit as x goes to infinity of this ratio. Now here is the idea. When we take the limit as x goes to infinity, if e to the x grows to infinity faster than x squared, then we would expect this limit to be infinity. In contrast, if x squared grows to infinity faster than e to the x, then we would expect this ratio, or the limit of this ratio, to be 0, right? Because the denominator is growing so much faster than the numerator, so then this ratio goes to 0. Okay, so that's the setup, and then the question is, what is the limit as x goes to infinity? Is it infinity or is it 0? That's the idea. Okay, well, obviously, the limit of this ratio of functions here is infinity over infinity. That's the indeterminate form. That's exactly the right scenario for using L'Hopital's rule. Okay, so basically what you want to do is answer this question rigorously. And by this question, I mean this question: which one grows to infinity faster? answer that question rigorously using L'Hopital's rule, and then explore the problem a little bit in Python. Now, I'm leaving this open to you. I don't have very specific instructions for what to look for in Python, what to visualize in Python. I want to leave that as an open exploration for you. I will show you my explorations in Python in a few moments. But first, I will now explain basically what happens when you apply L'Hopital's rule. So you apply L'Hopital's rule, we get the derivative of the numerator divided by the derivative of the denominator. That gives us e to the x over 2x. Now the limit as x goes to infinity of e to the x over 2x is still indeterminate, it's still infinity over infinity. So then the solution is to differentiate again, and the second derivative of e to the x, of course, is still e to the x. The second derivative of x squared is just 2. That's a finite number. So, it's a number that it's just a constant. That's what I meant to say. So then the limit of this expression becomes infinity over 2, which is just infinity. That is not an indeterminate form. So we just get that the answer is infinity when we apply L'Hopital's rule twice. That is a perfectly valid answer. We can get that answer. So that tells us that the numerator, e to the x, grows much, much, much faster than the denominator, x squared. And by the way, if you would set up this problem the other way, so you have x squared divided by e to the x, the conclusion would be the same, but the limit would be 0. You would basically get 2 divided by infinity, which is the same thing as 0. Okay, so here I'm showing my Python code, and this text here basically just describes what I already said out loud. Okay, so here, let's see. So here I'm defining the two functions, f of x and g of x, as NumPy functions. So we're just evaluating this function for these particular numerical values. And I'm making two plots here. One is a plot of the two functions individually, and then I'm also plotting the ratio of the two functions. And the question here with this figure is, what do the two functions look like and which one appears to grow faster? And then with the ratio, what we are going to look for is whether the line in this plot goes up to infinity or whether it goes down to 0. Okay, so now I will run this code here. And let's have a look. So here we see the blue line is e to the x, the orange line is x squared, and it's pretty clear even by x equals 3 that e to the x is growing faster than x squared. Very nice. And of course, both of these functions are going to continue growing as x goes to infinity. Then we see the ratio of the two functions here. Now, of course, your eyeball first gets drawn to this infinite discontinuity here at x equals 0, but ignore that. We don't care about that. The question that we are asking here is not about x equals 0. We don't care about the limit as x goes to 0. We care about the limit as x goes to infinity. And that, you see, this line is already rising, although that's not super obvious there. So I'll make this a little bit. How about 5? Let's set this up to 5. So now you see this is even clearer. E to the x is really starting to grow faster. And we're only at x equals 5. We're still very far away from infinity. And it's also clear from the ratio. The ratio is going up here. Now, what I encourage you to do, which I'm not going to do here, is change the order of the ratio here. So this is going to be, instead of e to the x divided by x squared, change this code so you have x squared divided by e to the x. And you will see that this quickly tapers down to 0. Okay, so now, maybe you think that this is not so impressive because x squared is not such a fantastically large number. Let's try x to the power of 20. Now what's going to happen? Again, the question is whether e to the x or x to the power of 20, which one of those two is going to grow faster to infinity? Let's plot this again. Okay, here we see it looks like the opposite pattern is emerging. Now, this legend here is wrong, right? I didn't update the label. This is really x to the power of 20. Here it looks like x to the power of 20 is shooting up to infinity really, really fast, whereas e to the x is basically, it looks like a flat line. It's, of course, not a flat line, but at this ridiculous y-axis scale, this looks like a flat line. Okay, and then here, again, this is blowing up to infinity as we get to 0. Ignore this. But here, it looks like it's going down to 0. So again, it kind of seems like x to the power of 20 is going to grow to infinity faster than e to the x. But wait a minute. Let's see what happens when we expand the x-axis. So instead of plotting to x equals 50, how about we plot, instead of 5, and let's go up to 50. Okay, here we get the same thing. So it still looks like e to the x is a flat line. But 50 is still a very small number when it comes to considering what happens when we go to infinity. Okay, now I'm plotting out to x equals 500. And now we see that e to the 500 versus x to the power of 20. Now e to the x is blowing up so fast. This is so steep here that now x to the power of 20 looks like a flat line. That's how insane this y-axis scaling is, 10 to the 217. Okay, so this scale is so ludicrously large that x to the power of 20 looks like a flat line. And then we see again, okay, here's the where we get the infinite discontinuity. And here, we can't even get up to, this looks like maybe it's around 90 over here. And the ratio of these functions just absolutely blows up. Okay, so why does this happen? And why am I so confident that no matter what number you put here in the exponent, eventually e to the x is going to skyrocket to infinity past, x to the power of 200? Well, here is the answer. The answer and the insight comes from L'Hopital's rule. And the general idea is that with L'Hopital's rule, we have to keep differentiating over and over and over again because we're going to keep getting the indeterminate form. Each time we differentiate, we're going to knock down the integer in the power by 1. And so eventually we keep differentiating over and over and over again, and we are always going to arrive at something of the form e to the x over c, where c is some constant. And now, depending on where you start, c is going to be a different number. Maybe it'll be 2 for x squared, or some like really, really large constant. But it doesn't matter. As long as this is a constant, then e to the x is always going to grow faster than any constant you can imagine. And that is why e to the x will always grow faster to infinity compared to any other power. And in fact, we can draw a conclusion here, which is that e to the x climbs faster than not every function. There are other functions that climb to infinity faster than e to the x. For example, e to the x squared will grow to infinity faster than e to the x. But e to the x will climb faster than any function that is non-infinitely differentiable. So any function that you can keep differentiating and eventually get to a constant, e to the x will climb to infinity faster than that function.